So now we'll continue putting together the basic foundational principles of quantum mechanics, and I'm also going to introduce the so-called Dirac notations, which are mathematical symbols Dirac introduced back in the early days, and these symbols turned out to be very convenient in doing calculations in quantum mechanics. So let me mention actually that as a practicing theoretical physicist, I noticed that an important component of putting together a new physical theory is to come up with the convenient and elegant notations. So these are not just some minor unimportant questions. So it's actually quite important, and having awkward notations could make our lives very difficult. So Dirac notations certainly satisfy the criterion of being convenient, and also they are widely used in the literature. So if you don't know them already, it's a good idea to familiarize yourselves with them, and this is what we're going to do today. But before introducing the Dirac notations and going further with the development of sort of more abstract quantum theory, I would like to mention a relevant superposition principle in quantum mechanics. So this so-called superposition principle simply states that if we have two solutions to the Schrödinger equation, psi1 of Rnt and psi2 of Rnt, their arbitrary linear combination, such as here with some arbitrary complex constants C1 and C2, is also a solution to this equation. So actually this so-called superposition principle is not specific to the Schrödinger equation. The superposition principle holds for any linear differential equation, which the Schrödinger equation happens to be. So there are no terms, which means that there are no terms like psi squared or psi cubed, etc. So, well, to prove this, one can just simply plug it into the Schrödinger equation and cancel the corresponding pieces term by term. So what this superposition principle motivates is the notion of so-called Hilbert space, which is a linear vector space where quantum states sort of live. To remind you, a linear vector space is a basic concept of linear algebra, which implies a set of elements that we call vectors, such that we can define a sum of any two vectors, and a sum of any two vectors itself belongs to this set, to this vector space, and where we can also define a multiplication by a constant, either real or complex, depending on the circumstances. And this sort of stretching of a vector also gives rise to another element of the set. So in other words, this multiplication and addition of vectors are closed operations. So per this superposition principle, we can suspect that whatever the mathematical objects are that describe quantum states, they also, in some sense, belong to a closed linear vector space that is what we call the Hilbert space. But what about the wave function that we have become already familiar with? So this wave function psi of r should be thought of in this abstract language and approach as a specific representation of a quantum state. We're going to discuss the meaning of it a little later, but here I just would like to mention that it's much like coordinates of a vector. So let's say if we have, in the simplest example, we have, let's say, a vector in 2 dimensions with some coordinates ax and ay. So these particular coordinates are specific to a choice of coordinate axis. So we are free to choose another coordinate system, in which case the coordinates will change, but the vector itself, in some sense, in some absolute sense, will remain the same. So likewise, in quantum theory, one can think about an existing quantum state which is sort of independent of our way to describe it. And if we choose to do so using the wave function, it sort of corresponds to the choice of particular basis. But there are circumstances, however, where we don't want to specify a representation. In this case, we could have called our vector state vector as psi with a vector sign on top, which would have been the usual notation in linear algebra. But instead of using this notation, Dirac found useful to use another notation presented here, which is so-called ket vector by Dirac. And also there is a bra vector, which corresponds essentially to psi dagger. And to tell you the truth, there is no profound reason for the choice of this particular notation. So they just turned out to be convenient to calculate matrix elements, etc., as we will see. And neither there is a profound reason to call them this way. Bra and cat vectors basically are called this way because when put together, they sound like a bracket, which sort of they look like. So now let me present a few embarrassingly simple facts from the basic linear algebra that I do expect most of you to know. But however, I'm still going to remind you of those because they're going to be connected to slightly more complicated structures that arise in the abstract mathematical formalism of quantum mechanics. So what I have here is simply a planar vector in 2 dimensions, some vector A. And if I have a coordinate system x and y with some unit vectors ex and ey, so I can write my vector as a linear combination of these unit vectors. So ex here is 1, 0, and ey is 0, 1. Or I can write it as so. So the vector and its conjugate. So another thing I want to emphasize is that if we consider the following structure, ex dagger plus ey dagger, understood as a matrix multiplication of these vectors, we're going to have 1, 0, 0, 0 in the first term plus 0, 0, 0, 1 in the second term, which when put together becomes an identity matrix. But very importantly, this result is not unique to the particular choice of this orthonormal basis. The result holds for any such orthonormal basis in any dimension and in any linear vector space. Now, the reason I'm telling you all this is because in quantum mechanics, so as we just discussed, so the state vectors, they represent elements in some Hilbert space, in some linear vector space, which we call Hilbert space. But in order to be able to work with these vectors, just like here, we need to introduce some coordinate system so that we have something concrete to work with. So in quantum mechanics, we have to define a basis. Since the Hilbert space is much more complicated in generally than this two-dimensional vector space, and most often we're dealing actually with infinite-dimensional Hilbert spaces. So the structure of the basis is generally more complicated. But nevertheless, the properties that we just discussed, sort of the simple properties of linear algebra, so are still remain the same. So for example, this identity that we just derived for this basis ex and ey also holds for the basis in the Hilbert space. So let's say if we have a set of vectors, either a discrete set or a continuum set, we will see both of them. So the sum of these ket bra products over all basis vectors gives rise to an identity operator. And this resolution of identity is going to be extremely useful for us in a number of derivations that we're going to see throughout the course. So for example, so this Q, I haven't really specified the physical meaning of this Q. It can be anything. So one example we're going to see pretty often is when we're dealing with the integral over volume of a product like this, where these vectors correspond to eigenstates of the position operator. So another thing I want to mention here is that any wave function, so what basis really means is that any vector in a linear vector space can be represented as a linear combination of the basis vectors. Just like here, I represented my vector A as a linear combination of ex and ey. So the fact that I have a basis here implies that I can represent my wave function or my state vector as a linear combination of these q's. And the matrix elements between q and psi is what we actually call the wave function in the q representation. So this is much like these coordinates. So these coordinates, for instance, here ax is can be written as ex dagger times a, and here psi of q can be written as a bracket product of q and psi. So, and again, in principle, we can have two situations. Either we have a discrete spectrum or we have a continuum spectrum. In the former case, we have a sum over q. In the latter case, we have an integral over q. But now a question remains of how to actually choose a basis or representation to describe our state vector, our wave function. Just like in the usual linear algebra, there is no absolute or correct answer. The choice of a basis is a question of convenience. But there is some standard or natural choices that can be constructed. And so I'm going to discuss now how it's done. So we already know that physical observables in quantum mechanics are associated with linear Hermitian or self-adjoint operators. For a generic such operator, one can define the eigenvalue problem as here, which basically is the problem of finding a vector or set of vectors which under the action of the operator don't really change but just are stretched with a certain eigenvalue A. And for the Hermitian and self-adjoint operator, these values of A are real numbers. So what's essential is that in many cases this set of eigenvalues of such operators form a basis in the Hilbert space. This means that we can expand our wave function in terms of these basis vectors. And the corresponding matrix elements, so let's say for this vector A, whatever it is called the wave function in the A representation. So one can construct an infinite number of such representations, just like there exists an infinite number of observables and corresponding operators. But sort of a natural way to choose a basis is to use operators that are relevant to our problem, such as, for instance, the coordinate operator, such as here in one-dimensional quantum mechanics, or the momentum operator. And the corresponding matrix elements, psi of x or psi of p, are called the coordinate representation and the momentum representation correspondingly. So, for example, psi of x or psi of r, we have already seen many times in our lectures. Now, the meaning of these basis vectors is essentially these tightly localized wave packets which are located in a precise point in space. So, in contrast, the vectors p correspond to states with a well-defined momentum, but which are completely delocalized in space. So these are completely different vectors, completely different bases, and which one to choose is entirely the question of convenience.